Let's do hydrocarbons crash course. In this today's crash course, we are going to see the nomenclature, alkanes, alkenes, and alkynes with the previous year paper questions. Without any further delay, let's get started. Let's quickly finish this. First of all, organic compounds are divided into open chain or acyclic, or closed chain, which are cyclic. In open chain, we have saturated and unsaturated. Saturateds are alkanes, unsaturated one are alkene and alkynes. In closed chain, we have homocyclic. Homo means same, right? And then heterocyclic. There we have further classification as acyclic and aromatic. Okay. So what is saturated compound first? Alkanes, which is completely saturated. It's not very reactive. Okay. The general formula is CnH2n plus 2, starting with CH4, C2H6, C3H8, and so on. Then comes unsaturated compounds, that is alkenes and alkynes. Alkene, the general formula is CnH2n. It doesn't have the first group, and the homologous series goes from C2H4, then C3H6, and so on. Alkynes, which will have CnH2n minus 2, which will have a triple bond, starting from C2H2, C3H4, C4H6, and so on. In case of cyclic system, as I told you, homocyclic, which will have same atom, like carbon in all the chains. That is homocyclic. In that case, we have alicyclic and aromatic. We already saw what is aromatic and what is aromaticity, anti-aromatic and non-aromatic in JEE division. You remember? Then heterocyclic means there will be another atom in addition to carbon. Like you can see, this is furan, thiophene, this is pyrrole, right? These are heterocyclic compounds. By the way, these are aromatic too. In heterocyclic, we do have alicyclic. Nomenclature, start with the root name, follow lowest equivalent rule to find out the correct nomenclatures. Alkenes are end with enes, alkynes are end with ine, alkyl groups, which is end with ile. So mostly R group refers for alkyl groups. And iso groups, which are CH3, two CH3s with the one carbon. Neo group, where is 4 groups attached with the one carbon. And primary, secondary, and tertiary carbons we know. Then start to name with the longest chain as your parent chain, and others are substituents. Give the lowest number to the substituent as much as you can. Like this. Give the preference to double bond or triple bond if that is present in the chain, either than the substituent present. Like pen 2 ine, pen 2 ene, pen 1 ene, like that. And in case of cyclic system, mention that is cyclic. So cyclopentane, cyclo-2-pentene, like that. And if there are 2 substituents present, go with an alphabetical order. Ethyl and methyl means first ethyl, then comes methyl. Then functional groups, this is the priority order. I'll be attaching the formula sheet or the single paper formula for the nomenclatures. You can check that out too. For functional group, starting from carboxylic acid, sulfuric acid, anhydride, ester, acyl halide, halides, amido, cyanide, aldehyde, keto, alcohol, mercapto, amino, and alkoxy. This is the preference order. Take the first preference group and then second one become a substituent now. Always give more preference to functional group than the substituent. Like you can see, ethyl 3-methyl 4-pentene noate. Okay, ester group is there, double bond is there. So we are including that chain, including both the functional groups in the parent chain. So benzene, that is C6H6, benzyl, that is the CH3 group on the benzene ring. Aryl is equivalent to benzene, but I have one bond to connect with another group, like an alkyl, which is C6H5. Then, as you can see here, the 2 and sixth positions. Let's say I'm having a substituent over here in the benzene ring. This position and this position are ortho. These two positions are meta and this position is para, while you are naming it as a common name. Let's talk about alkanes first. CnH2n plus 2. Mostly in entire organic chemistry you can see three types of reactions. One is addition, substitution and elimination reaction. So alkanes preparation side, you can prepare it using reduction of alkyl halides using zinc or lithium aluminum hydride. You can also use Grignard reagent to produce halides. Grignard reagent, how you can prepare it? Alkyl halide with a metal, it will form a Grignard reagent. So Grignard reagent with water, that will produce hydrocarbon with MgXOH. That is another method. Then hydrogenation, it is an addition reaction where from alkene I am adding hydrogens to form alkane. Then the next method is heating to form alkane along with sodium carbonate when I am treating sodium salt of carboxylic acid with calcium oxide. Then Gold's electrolysis, that is very important, where we can see RCOO minus, that is salt of carboxylate ion with H2O, that forms alkane, and CO2 as a anode side and H2 and KOH from cathode side. So as you can see, I have given the reaction of anode and cathodic reduction. Cathode means reduction, anode means oxidation happens. Remember, our hydrocarbon and CO2 belongs to anode, and KOH and hydrogen belongs to cathode. This can be asked as a question. Then Clemmensen reduction. Clemmensen and Wolff-Kirchner are like a twins, but the only difference is the reagent. Clemmensen reaction happens in the presence of acid medium and Wolff-Kirchner happens in the presence of basic medium. But the reaction is same. CO group will convert it to CH2 group. Clemmensen will not holds good for acid sensitive groups, and Wolff-Kirchner, in that case you can use Wolff-Kirchner where the reagent is hydrazine with the base. This is an example of acid sensitive group. Depend on the question, you can use it accordingly. Then the next one is Woods reaction. Alkyl halide with sodium, it produces higher alkanes. The problem with Woods is you can't prepare CH4 and you can't prepare odd number of alkanes. Always it will give you even number of alkanes. Then Franklin reaction, where same as Woods, here I am using zinc with alkyl halide to produce alkanes. Corey-House synthesis, alkyl halide with lithium in the presence of THF to give RLLi and lithium halides. And always remember, concentrated HI with red phosphorus will give you straight chains. This you might have seen in biomolecules also for the structural elucidation of glucose. ROH or RCOOH, that will give you the whole carbon system as a straight chain. Then talking about the properties of alkanes, always remember boiling point is directly proportional to molecular mass and inversely proportional to the branching. As the branching increases, the surface area will get decreases, so the boiling point will also get decreases. In case of melting point, obviously it is related with directly proportional with molecular weight, and other two reasons are also important, the packing efficiency. So if I can pack many things in a single place, so the melting point will be higher. And symmetry, if there is a symmetry, then the melting point will also be higher. Like you can see here, the first one will get more melting point than the second one because I can pack it like this. But for this one, it is not tightly packed, right? The cis ones will have lower melting point than the trans. Chemical properties of alkane. Free radical mechanism with Cl2 HNO, that will give you the possible place of replacing the hydrogen with halogens. Free radical mechanism is given over here: initiation, propagation and termination. Remember, in free radical mechanism you can expect many products. So the yield will be less. The yield of the major product will be less. Then nitration. I'm adding nitro group to the alkane. Usually these alkanes in hydrocarbons are less reactive than other groups. They are saturated ones, right? So upon reacting with HNO3, it will give you NO2 substituted compound, where NO2 will get substituted as in the more stable free radical place. Which is more stable free radical? Tertiary free radical would be more stable because of the inductive effect. Then comes secondary, then comes primary. So the order is important. Depend on that only the major product can be predicted. Then conversion reaction. This is a general format for the conversion reaction of alkanes, starting with CnH2n plus 2. That gives, wherever you go, conversion reaction, that will give you CO2 and water plus heat. But this is the reaction for alkanes, because you can see the formula is CnH2n plus 2. This can be asked in mole concept chapter also. In the conversion reaction, what is the relation? How much carbon dioxide is produced, or how much? What is the formula of the hydrocarbon reacted, like that. So you have to know this reaction. The amount of heat released for 1 mole of substance is heat of combustion. Heat of combustion is inversely proportional to its stability. As the stability increases, heat of combustion will get decreased. Next is oxidation. Oxidation of alkane will give you alcohol with the same number of carbons. This is particularly an tertiary alkyl to form alcohol. Tertiary alcohol. Then cracking. Cracking is the process where we are the higher alkanes are crushed or broken into lower level alkanes, like small alkanes. As you can see, propane. From propane we have formed methane, hydrogen and ethane and propene. Okay. Then important part is isomerization. Alkanes with AlCl3HCl. Remember the reagent AlCl3HCl. It will form isomerized products. Then alkenes. So alkenes will have CnH2n. CnH2n, C double bond C is there, sp2 hybridized. Preparation is very simple. Cracking of higher alkanes you can prepare, like we saw the cracking method. From alcohol, alkenes can be prepared by heating it up, which will remove the water. Remaining will be alkenes. Or you can use Al2O3 at 620 Kelvin or concentrated sulfuric acid at 440 Kelvin to form alkenes. Like you can see here, propane 2-ol to propene and tertiary alcohol to alkene. The mechanism of this dehydration is given. The major product will be formed based on the carbocation stability. Tertiary carbocation will be more stable, then secondary, then comes primary because of the plus I effect. So in case of elimination, you have to remember one rule, that is Saytzeff rule. That is super important. What it says, alkene with more alkyl groups, that is more substituted groups, that is your major product. Compare these two, pink and green one. The alkene with the more substituted, the pink one, which is having 1 hydrogen, 1 alkyl group. Another side also 1 hydrogen, 1 alkyl group. But in the green one, I have 1 alkyl group, 1 hydrogen and 2 hydrogens on the another side. So which makes the first one is more stable than the second one. It's not more stable, it's the major product formed. So that is what Saytzeff rule says. As you can see here, I have given you another example, which can form due to hydrogen hydride shift, 1,2 hydride shift. Then from alkyl halide, dehydrohalogenation also I can prepare. I'm using alcoholic KOH as a reagent. Always remember, this alcoholic KOH is the reagent for elimination. Don't get confused with that with aqueous KOH. Aqueous KOH is for substitution, alcohol is for elimination. So in elimination, again, the more substituted alkene is more major product. From geminal halide, geminal means the halides are in the geminal halide means halides are in the same carbon. Opposite to this, that is vicinal halide, which is in the adjacent carbon. Vicinal means halides are in the adjacent carbon. From geminal halide with zinc, it will form alkene with the release of ZnX2. Pyrolysis of ester. Pyrolysis means always happens at a high temperature. So it forms less substituted product as in your major product, forming carboxylic acid with alkene. This follows in Hoffman rule, less substituted alkenes are major product. Gold's method. Always in Gold's method we will be using salt of carboxylic acid. It can be of dicarboxylic acid or monocarboxylic acid. The product and the hydrocarbon and the CO2 from anode side, and the salt with H2 that from cathode side it will be produced. Then Cope's reaction of pyrolysis, where it will form alkene with hydroxylamine. Then hydrogenation of alkene. Remember, in hydrogenation of alkene, you can have two reagents. That is, one is linear catalyst, another one is bridge reduction. So bridge reduction always give you the trans product. Remember it like bridge for transportation, right? So bridge reduction will give you trans product and linear catalyst will give you cis product. So cis alkene and this is trans alkene. This is asked in previous year question papers a lot. So reagents, hydrogen, palladium with calcium carbonate and quinoline, that is linear catalyst. Sodium, lithium with liquid ammonia, that is trans bridge reduction. Then Wittig reduction starts with the formation of ylide to form an alkene. Properties of alkenes. As I told you, boiling and melting point, it's depend on the molecular weight. Melting point of cis and trans, if I am comparing, trans will be more than the cis. Then chemical properties, this can undergo electrophilic addition. Like this. So electrophile will get added on one side, another side will be nucleophile. Like you can see in Cl2 addition, Cl2 is forming in Cl plus and Cl minus, one will get added on one carbon, another one will be going to another carbon. So in that case, it prefers to be trans, the anti-addition. Okay, not trans, it's for alkenes. I meant to say anti-addition because as you can see the mechanism, particularly in alkene with the Br2 or Cl2, the halogenation part, the halonium ion for bromine, that is brominium ion, for Cl, that is chlorinium ion, will be formed cyclic state. Once it is formed, the another one will attack on the opposite side. So that's why the product is anti always. Okay, remember this. Like you can see, cyclic brominium ion intermediate has been formed and then it is attacking on the anti position. Then addition of HX. Addition of HX, it follows Markovnikov rule. What Markovnikov rule says? When you are adding HX to the unsymmetrical alkenes, the negative adenine will goes to more substituted side, right? So like you can see, the negative part, Br part, went to more substituted carbon and that becomes a major product now. Remember it like H will go to H side, more hydrogen side, that is less substituted side. Rich getting richer. Okay. These are the examples. This can undergo the rearrangement or shifting of hydrate can also be possible to form a stable compound. Then Karash effect or a peroxide effect or anti-Markovnikov product, where that will form in the presence of HBr and peroxide combo. in case of HX addition. So it's just opposite to Markovnikov. Negative part will go to less substituted side. Like you can see, this becomes our major product. This is minor. This works well for HPR with peroxide combo only, not with HCl and peroxide. Hydration using dilute sulfuric acid, where H and OH addition, it is also a Markovnikov product. That is a major product. Then oxymercuration, demercuration, again HOH, Markovnikov product, but anti-addition. Addition will happen on from the opposite side. Again, the mercury will be forming an intermediate over here to form the product. That's why anti-products. Then hydroboration. Here the product is syn addition product, but anti-Markovnikov rule is followed. As you can see here, peroxide is there. You can remember it easily. Simon-Smith reaction, where CH2I2 or CH2X2 dihalo compound with CH2, that forms in cyclic alkanes. Then oxidation using KMNO4, in gold alkaline KMNO4, it is forming an OH-OH substituted on both the sides of the double bond. This is an syn, happens on the same side, not on the opposite side, because KMNO4 attack will happen like this to form the product. The same kind of attack will happen with osmium tetroxide also to form same side attack, OH and OH to the same side. Then epoxidation with the MCPPA, it forms an epoxide. Later it is forming an OH and H attack on on the opposite side. So anti-product is formed. Ozenolysis, I have told you so many times, break the double bond, put double bond O, double bond O. If that is reductive ozenolysis, which will give you carbonyl groups like CHO and RC double bond O. The mechanism of ozenolysis is given over here. Then oxidative ozenolysis, where that will give you oxidated product, that is carboxylic acid, where I am using H2O. Diels-Alder reaction, that is 1,4 addition for a 4+2 cycloaddition happens with diene and dienophile to form the product. Bromination of alicyclic part using NBS, N-bromosuccimide, which will give you the alicyclic hydrogen will get replaced by bromine. As you can see, it will attack, NBS will only attack the alicyclic carbon. The next one is alkynes, which is having CnH2n minus 2. Let's start with the preparation. From trans elimination of halides, alkyl halides, we can prepare alkynes using alcoholic KOH. See, here also we are using alcoholic KOH, which does elimination. Then vicinal dihalides, we can remove the HX as from the anti-position to form alkynes. Then Gold's electrolysis, again, here I am taking an dicarboxylic acid with the double bond of alkenes to form alkynes. Using Grignard reagent with acetylene, it gives us R added, alkyl group added within acetylene. So depend upon which alkyl group you will choose, that will get added over here. Along with that, you can see the methane, that is alkane group formed. From calcium carbide also you can prepare acetylene, and using iodoform 2 molecules and 6 Ag also you can prepare acetylene. These two methods for acetylenes. Then properties, this is a non-polar sp hybridized, so there will be more S character, more acidic character and more electronegativity. Chemical properties involves the electrophilic addition first with Cl2, FeCl3 in the presence of FeCl3. Why FeCl3? Because that can act as a catalyst to prepare an electrophile from Cl2, which can replace all those hydrogens from alkynes and alkenes. Addition of hydrogens using nickel hydrogen. You can add the hydrogen on the alkene and alkyne chains to form alkanes until it is becoming a saturated form. Then Lindlar catalyst will give you cis alkenes and then bridge reduction to give trans. In addition of HX, the reactivity order follows. HA will be more reactive, then comes HBr, HCl and HF, and it can form the geminal halide. Addition of HOX like HOCl, which will give you RC double bond O with CHCl2. The mechanism is given over here. These are electrophilic additions. Talking about nucleophilic addition, using dilute H2SO4, HOH will get added. Later it will form enol to keto form, that is CH3CHO. Then addition of HCN, which will give you cyanide substituted compound, and oxidation or combustion, that will give you carbon dioxide and water plus heat. This is a general reaction of alkynes. Using KMnO4, you can do the oxidation to form a dicarboxylic acid, in particular of alkynes. And CH3C triple bond CH, upon oxidation it gives two different carboxylic acids. Then ozonolysis, I told you in alkenes, the ozonolysis break the double bond, put two bonds on the on the alkyl carbon. Here, don't break all three bonds, just break two bonds and put double bond O. Later by the hydrolysis or the oxidation, you will get carboxylic acid. Okay, but don't break the bond entirely, leave one bond. In the alkyne, it will not break completely. That is a very important clue point. In some questions they will give you, this will give you two different compounds, or this will give you two compounds. So that you will get to know that is an alkene, not an alkyne. Okay. Let's solve this previous year questions from hydrocarbons. Total number of sigma and pi bonds respectively in hex 1 ene 4 ine. This is a very simple question. If you know the nomenclature, you can easily answer to this question. Let's do this. Hex, first draw hex. 1, 2, 3, 4, 5, 6. 1 ene. 4 ine. So this is 1, 2, 3 and 4. So 4 ine. So how many pi and sigma bonds are there? As you can see, 1, 2, 3 pi bonds and 1, 2, 3, 4, 5 sigma bonds. Don't write like that, please. Check the sigma bonds attached with hydrogen as well. So here I have 1, 2, 3. So CH, this is CH2, carbon, this is carbon, this is CH3. So already I have 5. So which is 5 plus 3, 8, then 10, 11, 12, 13. So totally 13 sigma bonds and 3 pi bonds are there. Okay. Please don't forget the hydrogens and the bonding. The next question, the given below are two statements. Statement 1 is ozonolysis followed by the treatment with zinc H2O of cis-2-butane gives ethanol. And the statement 2 is the product obtained by ozonolysis followed by the treatment with zinc H2O of 3,6-dimethyl oct-4-ene has no chiral carbon atom. So we have to check by doing the reaction. Treatment of cis-2-butane. So I told you, whenever you are doing ozonolysis of double bond compound, ene compounds, break the double bond, put double bond O, double bond O. So we will ended up with CH3 CHO, that is two compounds. which is ethanol. That's right. And the product obtained by ozonolysis followed by the treatment of zinc H2O. See, I had gave a trick. Break the double bond, put double bond O. It only works for zinc H2O. Okay. Reductive ozonolysis. Zinc H2O of 3,6 dimethyl octforane. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 3,6. 3, 4, 5, 6. Dimethyl octforane. This is 3. So this position becomes 4. Diene. So upon doing ozonolysis for this, break the double bond, put double bond O. 1, 2, methyl group. Here I will be having CHO plus this side CHO bonded with methyl group. This. They are saying that has no chiral carbon atom. Let's check. This CH3, CH2. This is CH. This is chiral. Here also the CH is chiral. So there is a chiral carbon present over here. So statement 1 is true, statement 2 is false. Moving on to the next question, the given reactions identify the reagent A and reagent B. Okay, let's see the reaction. Toluene is treated with anhydride to form an intermediate followed by forming an aldehyde. Okay, and again toluene with BCS2 intermediate and then again the same aldehyde. So what is this reaction? You remember CS2 with one reagent that will form aldehyde, which is étard reaction, right? Similarly here you can see anhydride with toluene, which will form the intermediate as benzene ring with the CH, and this part will go and attach over there, COCH3 twice. That is the intermediate. After hydrolysis you will get aldehyde. So I'm giving you A. In the étard reaction, what is B? Just let me know in the comments. So A is CrO3. Tell me what is B. The reaction is étard. Current reaction, identify H2 with A, palladium carbon gives this. Okay. Then H2 with CH3, C triple bond C, CH3 with H2 in sodium liquid ammonia. Okay, gives B. So we have to find A and B. So what is the first reaction? So what it must be? It must be an alkyne so that it can form alkene, because only 1 mole of H2 is involved over here. So A must be an, here I don't have anything, so that is a triple bond with CH3. This is A. That is butane, right? And then B with the H2, which will form, again HH will get add, but there is a important thing about this particular reagent. What is this reagent? What cis form or trans alkene will form? That is an importance of this question, because the options given as 2-pentyne, N-pentyne, 2-pentyne, N-pentyne as A. So this is C2H5. Okay. So pentyne, that is fine. But what about B? B is important. They have given trans to butane, cis to butane as your options. So this particular reagent, that is bridge reduction. Remember? Lindlar catalyst bridge reduction, right? So which will give you trans. Remember, bridge is like a bridge, so which uses for transportation. So trans. So it will always give trans to butene as your answer. Then the next question, the one giving maximum number of isomeric alkenes on dehydrohalogenation reaction is maximum number of isomeric alkenes. So what are the options given? It is 1-bromo-2-methyl-butane, 2-bromopropane, and 2-bromopentane, 2-bromo-3,3-dimethylpentane. So let's see one by one. Butane, 1, 2, 3, 4, 1-bromo, 2-methyl, and the second one is 2-bromopropane. What they have given is isomeric alkanes on dehydrohalogenation. So we have to remove halogens from this. So which I'll be ended up with butene, and then 2-bromopropane, which again terminal alkene, 2-bromopentane, 1, 2, 3, 4, 5, 2-bromo. So either it can form terminal alkene, or it can form alkene from this, right? And the last one is 2-bromo 3,3 dimethyl pentane, 1, 2, 3, 4, 5. So 3,3 dimethyl 2-bromo. So this can give, Br will leave from here either let me write it as the same way. It can form the terminal alkene, or here I don't have hydrogens, so obviously it can't leave from here. So if there is only one methyl group, then there is a possibility of forming a major product. So let's see out of this which can form geometrical isomers. So this alkene, this is a only product. So this can't exhibit any isomer, so only one. In this case, I can have this can't exhibit, but another product can exhibit cis and trans form. This is terminal alkene, so no chance. This is the first one is also the terminal alkene, so no chance. So answer to this question becomes option C. Find out the major product for the following reaction. The reaction is given as CH3 with OH with H3O plus. What is the major product? And the options, look at the options. As you can see, majority of the option involves the ring expansion. So let's see how it goes. Obviously OH is there, H3O plus. So what we can expect is OH as the first step, it will up hydrogen and OH leaves the compound. First OH leaves the compound, so that here it is forming a positive charge, right? So if this one breaks, this will have negative and this becomes positive. So let me number it. 1, 2, 3, 4, 5, and this position becomes 6. So 6-membered ring, 6, 5, 4, 3, 2, 1. In the first position, I have a methyl group, and in the sixth position, I have another methyl group. This here, that is in CH. So this is CH. So this CH, when one hydrogen leaves the compound, because I'm having positive charge over here, if it leaves the compound as H plus, remaining I will be having minus charge that will get combined with the positive charge to form double bond. So answer to this question is option B. Clear? A hydrocarbon X with the formula C6H8 uses 2 moles of H2 on catalytic hydrogenation of its 1 mole. On ozonolysis, X yields 2 moles of methane dicarbaldehyde. The hydrocarbon X is. Okay, so that is C6H8. And also the 2 moles of H2 on catalytic hydrogenation of its 1 mole. 1 mole requires 2 mole. So which means there must be a alkene or 2 double bonds in it. Right? If we find out DOU, we'll be getting 3. So which means there is a ring and 2 double bonds. On ozonolysis, X yields 2 moles of methane dicarbaldehyde. So break the bond, put double bond O, double bond O. If you find DOU, degree of unsaturation, you will be ended up with 3, which means C6H8 is there, there must be a ring. So 2 moles of H2 on catalytic hydrogenation for 1 mole. So 1 mole requires 2 mole of hydrogen, which means 4 hydrogens. So either alkyne or alkene. So since the DOU is 3, I'm assuming that is alkene. So let's check with the options also. Hexa 1, 3, 5 triene. Okay. So in 3 positions, if I have triple bond, and the next clue is ozonolysis yields 2 moles of methane. So there is a double bonded compound which got break, right? So which cannot be a triene. Let's check for option B. 1-methyl cyclopenta 1,4 diene. Cyclopenta. 1-methyl cyclopenta 1,4. 1, 2, 3, 4 diene. In that case, if I'm breaking the double bond, it will not give the same molecule twice. There should be a symmetry so that it can give same molecule. What about cyclohexa 1,3 diene? 1, 2, 3. So in that case, if I am breaking the double bond for ozonolysis, it will give this part as 1 double bond and another part is not showing any symmetry. So same product can't be formed. What about the last option? Cyclohexa 1,4 diene. Here you can see if I am breaking this, I'll be ended up with, so double bond O, double bond O. This side also the same thing. If you don't know what is methane dicarbaldehyde also, you can solve this question. Right? But you have to have a basic understanding how ozonolysis works. So answer to this question is cyclohexa 1,4 diene. Moving on to the next question. Number of bromo derivatives obtained on treating ethane with excess of Br2 in sunlight. Ethane. So CH3, CH3 with Br2. So what are the products can be formed for bromo derivative? They didn't mention there is monobromo or dibromo or tribromo. So instead of hydrogen, you can replace it with bromine. CH2Br plus CHBr2 and then CBr3 with CH3 and then CHBr, CBr3 plus it can also give CBr3 CH, this is CH2Br, this is CHBr2, and CBr3 CBr3, and other products can be CHBr2 CHBr2. What else can be found? CH2Br CH2Br. And there is another possibility. You can just try out with replacing all those hydrogens. That's it. So another possibility can be CHBr2 with CHBr. So any other possibility? One monobromo products, two dibromo, two tribromo, two tetrabromo, one pentabromo, and one hexabromo products. So totally 9 products can be formed in this reaction. Okay. And the next question is product of formed in the multi-step reaction. The reaction is CH3 CH double bond CH2. Yes, the first one is B2H6, second one H2O2 with NaOH, third one PCC, fourth reagent is CH3MgBr. Simple reagent, let's see one by one. First one B2H6. B2H6 borohydration, right? So which will lead to CH3 CH2 CH2OH, right? Anti-Markovnikov, presence of peroxide. Altogether this product. Then with PCC. PCC is an oxidizing agent. With PCC, that is a mild oxidizing agent, so CH3, CH2, CHO will be formed. And in Grignard reagent, it will get attached on the carbonyl carbon. So CH, CH3, CH. Right? So this is the answer to this question. Since the hydrocarbon chapter involves many reactions, please be thorough with those reactions. Keep practicing more and more questions and let me know your doubts.